company that has been doing some pretty amazing things lately, including building the Pact contract language, which makes it easier to prove properties about your contracts, which is pretty nice if you don't want to lose all your money. And he's also a musician, and he's built some Haskell tooling for music. And this talk, he's going to bring together those two sides of his experience and share with you some experience about how to use Haskell, both in production and for your hobby. So, take it away, Stuart. Give it up, guys.
Thanks, Ryan. Hi, everyone. So, thanks to Ryan and Doug for setting this up, and Gershom and all the people who work on the New York Haskell. And thanks to Digital Asset for hosting this. It's really cool. So you heard about me. This is a kind of a funny talk that was part of a music talk. It's going to be part of a music talk until I realized it would make my talk 2 hours long. And then it came back into my life, the thing that I was working on as part of what we're doing at Cadena. So I was like, all right, it's time to come talk about this. And it's super nerdy. So, yeah! Because it's about parsing. So imagine you're a new Haskeller and you come onto the Haskell IRC and you want to know how to do regexes, because, of course, in any language, the first thing you want to do is, where's the regex library? You want to get something done. So you say, hey, any pointers on good regex libs in Haskell? Thanks. And SHW, points for what SHW stands for, by the way. Yeah, parsec. And so the noob says, cool, and then he comes back, about 20 minutes later and says, wait, where's the regex part? How am I supposed to handle text? And he says, regex can you deceive you, stretch out with your feelings. Obi-Wan Kenobi? All right, so goes and writes the entire app in Bash and gives up on Haskell. So that's kind of the story of regex and Haskell. No one knows what SHW stands for?
Super Haskell warrior.
Nope, smug Haskell weenie. Shout out to Emily on that one. All right, so parsing is like a greatest hit of Haskell. It's one of the things that makes us smug, because it's one of the reasons why we're just not afraid of writing languages. Because it's really one of the things that, in any other language, you're like, yeah, but you'd have to write a parser. Nobody wants to write a parser. And whereas in Haskell, the selling point is that you can write parsers, you can write code that looks like BNF, that actually looks like the specification of language. This is an actual list parser that we are using at JP Morgan. That's the whole parser. The main elements that it's comprised of, so this is, this is kind of, his volume good? It's too loud? Good. Alternative is kind of the main one. This guy, which allows you to, say I want to do this or that, and then some kind of primitive combinators to say some is a really important one. Some or many. Some means that a bunch of things, but at least one. Many means a bunch of things, can be zero. Some other things from the Haskell zoo come in, like functor. Applicative is has a very natural home in parsing. Monad plus is kind of the easiest way to describe that, parsers need to be able to fail. You need to be able to look at something and be like, nope, that's not, this is obviously something else, fail to the other alternative. And then there's some kind of classics that are, part of any parsing library. Set-by is something that makes it really easy to say, I want a bunch of things separated by commas, or something like that. So that's just for those of you who haven't looked at parsers. And the other thing to say is that parsers really are easy. So that whole thing of oh God, I have to break out a parser, just do it. Because it's really not that hard. Parsers are they're just incredibly useful. And the other thing about parsers that are really interesting is that the dog fooding that goes on inside the parser libraries is really deep. So something in this first example, we had this thing called, so obviously one thing you want to do in Lisp is capture a list with parens around it. And so it's just parens, a combinator called parens is a function that takes another combinator that's using except-by. I just wanted to give an example of how easy it is to write parens using all the things that I just showed. given some char parser that has that basically has a predicate that allows you to test a character to see if it's what you want. And something called char, which says, am I looking at A? Am I looking at B? You can write parens just like this. You say char open parens, ignore that, parse something in the middle, parse parens after it, and ignore that too. And you're done. And that's literally the definition of parens in a lot of parsing languages. So the point is it's really a very small amount of ingredients that make it into something where you can have something like this expert data structure. You can have a very small production like this with a few extra things. And then you could take some Lisp like this, right? You can take some Lisp, and what you can see is you can take this and you can get this. And the idea, Lisp is a good example because Lisp looks a lot like the AST that you will produce. Other languages obviously have things like infix, and that can get more tricky. But the whole motivation is that you've got something that looks like this. You want to end up with this. Break out parsec, break out megaparsec, and you'll get it done in a couple hours, and it'll be very robust. So that's that's just kind of like an introduction to parsers and an encouragement for people to really use them. And, I mean, really for the smallest job. Like that's the thing. People are like, oh, well, I don't have a language here. I'll just like take a few characters and like pattern match on. Just use a parser because that way it's future proof. You're ready to add more complex syntax. All right, so now we can talk about my war, which was MusicXML. And I don't know how many Black Flag fans we have in here, but there's a great song by Henry Rollins called My War. It's Henry Rollins in the middle. And the idea is that I wanted to get to here, which meant I had to go through here. And anybody who's ever done XML knows that it's going to war. I mean, it's just, XML is horrible. So, and Haskell isn't particularly great. I mean, it's fine, but it's just one of these things that nobody really ever wants to deal with. So the problem is I've generated a bunch of music data. I need to perform it with humans. So I have some ideas about how I can organize notes and put together a nice composition, but nobody's going to play it if I don't write it out to sheet music. There's some other options there's one called Lily Pond that really jumps the shark. It's actually like a mini DSL for writing scores. It's like, I'm going to take this and now I'm going to turn it into another language. It's good for directly scripting. It's not right. Music ABC is very trivial, so that means the solution is MusicXML. There's tons of printing support. It's supported by these applications that can, produce beautiful sheet music. And back when I was doing this stuff in Java, there was a thing in Java called Jaxby, which could basically suck up an XSD, an XML schema, and produce. It was horrible to work with, but at least you knew that it would always produce valid XML. So in Haskell, what do you do? You use a hand-rolled MusicXML emitter on Hackage. And every one of them, they only implement whatever the author got around to. So if the author was really into, most of them have notes and staffs and stuff like that, but one person might be like, I don't really need repeats or something like that. Second, it meant that to use it, you'd have to use whatever, it imports whatever metaphor the author wanted to express music in. And, I mean, I'm doing this coding for fun. I don't want to, I want to invent it. I don't want to use somebody else's library for that. So also, for what it's worth, MusicXML is now at version 3, so these are starting to get very old and crusty. So I have a terrible idea, which is it's fully specified in XSD. And I actually found, I think it's Haskell, one of these, has like a weird library that'll actually like look at an XSD and try to spit out a bunch of Haskell data types representing the types that are essentially expressed in XSD. That had been abandoned since 2011, and when I pointed at the MusicXML XSD, kind of predictably blew up and couldn't handle it. So great, I'm going to generate a MusicXML library from XSD. I need to generate a DSL that will always correctly spit out the XML. The whole point here for me is completeness. I want to not be like, oh, I need to do this weird notation and it doesn't exist. So I want something that's just going to spit out the whole XSD. I want to load it as an AST, and and then basically to do that, I need to have something that can read XSD, that can recognize streams of XSD coming out, because XSD is just XML, but it's XML that specifies a schema. So what I'm doing is I'm taking in XML, but I kind of want to have combinators to help me deal with the XML. Sounds a lot like a parser. So in this attribute group and adders, these are two XSD productions, attributes and attribute group. What I ended up with, I just want to kind of motivate this from the start, is that I ended up with something that looks a lot like a parser. You know, I'm building things as I go with applicative constructions, and then I'm breaking out the individual combinators to recognize the XML that I intend, that's supposed to be there. It's supposed to be parsing correct XSD. So, you know, it's a very good way to go. So, how do you do this? Really, for my first pass, it really wasn't hard. I basically just needed StateT. So I just needed to track state as basically a stack of XML elements. And I needed a monad error instance. I needed to basically be able to break out and say, oh, this isn't what I'm looking at. Try another alternative. And what's great is that by just using StateT Except, I get all my instances. I get alternative. I get optional, which is defined in control applicative. Optional is nice if you have like a maybe in your data structure. You just put optional around in your combinator and it just matches right up. You really got running pretty fast with that. You know, I had to do some hacking to like dive into XML, you know, basically dive into the child element. But I built the DSL emitter actually quite fast. The code gen was the worst part. It made a monster Haskell module. It took a 4,500 line XSD, turned it into 8,000 lines of Haskell spaghetti. And most importantly, I shipped the piece. I was actually able to get Haskell spitting out 100% conformant music XML, and went and performed the piece, released an album, which was the topic of my last talk, the way I actually composed that piece. One thing though is I wanted to actually be able to read the music XML, because then it turned out that there had been some weird idiosyncrasies in my old Java version, and I wanted to see what those are, so I wanted to read them back in and be able to compare what the Haskell was producing and Java was producing. One thing about my solution is it didn't preserve element order. It was basically just a search. If you were looking through a body of like XML elements, it would be like grab these, but it didn't really know what the order was in. And it turned out that just using except didn't really give me good failed semantics. So the second one, my second iteration was to use, this is great by the way, text XML in general is what you should use for XML. It's like low level, it just works, it's a very small library, it's great, and it comes with a cursor. So cursor is the kind of co-monadic way to, you know, happily traverse your XML and maintain a kind of sane state. So this allowed me to generate readers. So alongside of the data types that allow me to emit XML, I can now put a reader next to it that would read XML and produce that same data type. Because when I loaded in the old one, all sorts of terrible things happened. So then I had a two-headed beast. I had this new parser that worked in the code gen reader. I had the old parser reading the XSD. I tried to go in like dog food and replace it into the other one, and it didn't work. And I actually really wanted to go all the way down and like turtles all the way down to the original XSD and make it that, because I had to hard code all the XSD basic parts, and I wanted to actually just dog food the whole thing and make it that. It turns out that XSD is actually you know, a fraud. It's like it claims to have an XSD for itself, but you know, there's no compiler. There's nothing that's, you know, there's no like, no bootstrap. So it's just, there's a bunch of stuff in there that are basically magic incantations. So that never happened. So that was that. That library's up there. It's called FabNoXML. If you ever need to do music XML, it does actually work. And it covers the entire music XML spec. If anybody feels like working with XML, you could go in and finish the job and do the XSD, but I wouldn't wish that on anyone. Fast forward 2 years. I was actually doing this while I was at JP Morgan, because that's when I was learning Haskell. At that time, that was when I started working with parsers too, because right around that time was the same time that we started thinking about smart contract languages then. and wrote a little Lisp for the Juno, for the blockchain we had there. But it was really very primitive. Left JP Morgan, founded a company I'm at now, Cadena. And the first thing we did was produce a private blockchain, and we needed a smart contract language. Wrote a smart contract language. First cut took about a month. So again, this is one of these things why Haskell is so great. It's like I have some experience writing some programming languages for users, but the point is that you can do things in Haskell that that people in other programming languages would just be like, oh, you should never do that. Was able to ship it in 5 months. So what is Pact? Pact is a Lisp or sexp, S expression is what sexp means. Syntax smart contract language. I say that because a Lisp usually imports the notion of macros, and it usually imports the notion of lambdas, two things that are not in Pact. It's part of our blockchain platform. One of the big things it offers is a key value DB metaphor and native support for public key authorization. It's Turing incomplete, which is kind of an interesting feature. In other words, if you have a function, no matter how long it is, if you have a function A calls function B calls function C calls function A, it'll fail to compile. It'll detect the loop and it'll prevent you from doing it. And it doesn't have lambdas because with lambdas you can, yes, write a Y combinator. And so the whole idea was just wanted to make it that there's no way this language within a given transaction can be Turing incomplete. It means that all paths are final, that you can specify the entire AST trivially. And in fact, in Pact, we use this for performance benefits. We actually, like, if you import another module, we actually, when you load that into the blockchain, we actually import all those symbols so that the definitions are actually in place when you execute the code. So Pact actually executes very fast. This is an example of things like Turing incomplete can actually result in performance benefits. It's got some nice nifty features. It's got type inference. The types are somewhat, they're somewhat inspired by typed racket a little. It's got partial application, kind of Haskell style partial application, where you don't need to use a partial keyword, map, filter, fold, compose. And then finally, because it's Turing incomplete, we're able to compile it directly to SMT-lib2, which allows us to, and then we've designed an embedded DSL, which is a very important part of the plot that we're getting to here, is this embedded DSL. And the idea is that it's great that we can compile a Pact program to SMT-lib2. The problem is that we now want to declare properties about our code that we want Z3 or a similar SMT solver to show us that they are always true or give us a model for how they're false.
So they didn't know which abstract computational device can accept this language. It's not a Turing machine, is there some intermediate thing?
Oh, I was trying to remember. That's a great question, and I wish I knew the kind of right answer for it. What do you call that?
Model for computation, I suppose.
Right.
Class of languages or something.
This is the question I've been trying to formulate to Emily for.
So there's kind of a hierarchy of languages that can be accepted by the overall abstract devices. Turing machine would be the largest, but they're well defined.
This is somewhere between the yeah. So it's right in between where we don't actually.
You mean system F?
No.
What just happened?
You think about like an SQL.
So what's the answer?
STLC or readable.
Those like weakenings of lambda calculus, because that's like the whole other side is lambda.
So you have the untyped lambda calculus, which is your Turing, sort of like general lambda calculus. Then you have three operations, right? You have application, lambda abstract, and variable instantiation. And synthetic lambda calculus has that sort of weak type system on top of it, and it's created to form a Turing complete rewrite system on top of it. So untyped lambda calculus, right? That's your type system. Illegal there is an exception now, which includes Turing types, and system F on top of that has things like generalized function types, right? And we sit somewhere between that and nowhere, and so the type learning type.
The reason why I wanted to digress on this is I gave a talk on Pact in Boston Haskell, and someone asked this exact question. I just went. Sure.
So I don't understand this question. Answer I just heard. Is there a name for the kinds of machines?
The machine is what, yeah.
Oh, okay, yeah.
I'm not sure.
Now, when you say machines, you mean like SCCD and things like that?
No, like trying to speed or down. Yeah.
I think it's probably, yeah, Shane, I think you mentioned something. So, right, I'm not the guy to answer that question. I'm a guy who built my background in languages comes from building a DSL for JP Morgan that its big claim to fame was that it was also Turing complete, it was also point free, it had no variables, and it made tons of money. And it also had non-programmers writing it. So so one of the big goals in Pact actually, Pact isn't Turing complete, or is Turing incomplete, not just because of like some kind of like arbitrary blockchain, bonus point. It was also to make it that it was like that the programs, it was a way to constrain logic to try to make the programs very easy to understand and kind of like point people in the direction of what a transactional system should look like, which is that a transactional system should terminate fairly quickly, in the sense that a lot of what you're trying to do on a blockchain is you're basically trying to manifest some kind of real world or human interaction or something like that. You basically want to do that as fast as you can and as correctly as you can, as opposed to implementing something like a generalized auction or a some kind of like non-deterministic exchange or something like that. Like that stuff probably shouldn't be in a blockchain. The results of the trade should be on the blockchain. So that's kind of the opinion behind it. So Pact in its first outing obviously had a parser. Oh yeah.
Do you also do a lot of recursive inlining because you just allow recursion?
Yes, that's what I was saying. Is that when we load a blockchain, when we load it into a blockchain or into some kind of, we take a body of code so Pact kind of, like a lot of smart contract languages, Pact kind of differentiates between a body of code that gets loaded and then transactions that execute the code, although they're actually exactly the same. So they're kind of like two run modes, and one run mode is loading code. And so when we load a module of code, the first thing we do is we go through and build the graph of all the references. Well, since we've already resolved all the references, we just take the actual, the binary representations of those function definitions and just stick them right into the ASP. So it's actually one of the reasons why it was so easy to compile to SMT-lib2, because that's something you have to do if you want to admit a program, is that you have to resolve all references, you have to unroll loops. Well, we do have loops, and we have map, filter, and fold, so we have loops, but getting back to parsing, first version of Pact had a parser. Parser did quite a lot. It recognized a lot of, it was very kind of Pact focused, recognized a lot of syntax productions in Pact. It was written in parsers, which is a very interesting library, written by Ed Kmet, that allows you to kind of defer your choice of which parser library you want to use. And the justification for that here was we wanted to use, Ed also has this library called Trifecta, which its kind of big claim to fame is that it has really, really nice error messages with little carrots that like point exactly, it gives you the code, it gives you little carrots that show exactly where the error occurred, they're in color. As opposed to parsec, which, errors are okay in parsec, but they're not really that great. But it's slow. Trifecta is not a particularly fast parser. And then use parsec on the blockchain. So we have a bunch of combinators, and they work on parsec. They work on Trifecta, they work on parsec. They do not work on megaparsec. There's a library on Hackage for instance that provides instances, but I had some problems with it, and I think it's a kind of abandonware. So anyways, parsers is an interesting library to look at just if for some reason you want to kind of defer the choice about which parser library you want to use. So parse, we make a thing called exp, and then we have a compiler, and I put compiler in quotes because Pact barely compiles. Pact, one of the promises of Pact is that since it's an interpreted language, we don't want the representation of the code on the blockchain to differ significantly from the code you actually wrote. So think of like SQL or like stored procedures or something like that. If you introspect stored procedures that you've put onto a database, the code is right there. Now, of course, it might have done some optimizations, but it's an interpreter, it's an interpreted language, and so when I say compiler, what we're really doing is we're just taking this parsed form and just introspecting on it a little bit further, mainly because we don't have macros. So like if you know anything about Lisp, a lot of Lisp is actually built in the Lisp macro system. And since we left that out of Pact, we have a lot of what compiler is doing is basically providing the special forms that we see in Lisp. So that's why I put compiler in quotes. I mean, it is a compiler, but compiler means different things to different people. So how do we do the compiler? We've got an exp, or we've got maybe a bunch of exps. And so, one of our productions is defconst. It's kind of a typical Lisp production. And what we would do is basically pattern match. If you have a sexp, we've already matched on defconst, so now we got the rest of it. And we're basically pattern matching on the list shape that we're looking at. And maybe capturing the rest of whatever's in there, and then just building things kind of by hand. So it's basically pattern-based recognition. It's not the worst. It actually works pretty well. I mean, you can work pretty fast with that, but it's hard to reuse pattern matching logic. Pattern synonyms are powerful, but they are not as general. Pattern synonyms are they're kind of macros, really. They're not full-on logic. They're not like combinators. I don't think you could say pattern synonyms really function as combinators. And then things that are hard to factor, like if you were to look at this code and you're like, oh, I'd actually like to take this mcconst, even just taking this and making a top-level function, you've got all these arguments now. You don't really know what they mean. The factoring just gets kind of irritating. But it was fine. The big advantage of Pat is it worked and it was fast. Pattern matching in Haskell is fast. GHC eats it for breakfast. And the compiler was, not any kind of performance concern. One thing about Pact is that on a blockchain, parsing and compiling, if you're an interpreted language, it's obviously a concern. How fast do you do that? So we have performance in the back of our mind when we're thinking about things like parsing. The reason why I say that is the programs in Pact are not that big. So we don't have to worry about like Haskell-like build times. We're going to have very small programs, but even those small programs are going to impact the blockchain's ability to transact. So we want those things to be as fast as possible. But getting back to the idea that we want to do formal verification, and we wanted to put, so the idea again is that we're compiling Pact to SMT lib2. That works. It was one of the reasons we put in a Hindley-Milner type system, is that it needed to be strongly typed, but types in Lisp, from a syntax point of view, are kind of ugly, so a Hindley-Milner system ended up being a very nice thing to do. So for instance, this function specifies the arguments of all of its specify the types of all of its arguments, but doesn't specify its return type because it's a side effective function. It happens to return a string, but the string is just like transfer success. So you specify the types that are important to you, and then we have a type checker that'll tell you if you've got a fully typed AST, which you need in order to execute, to be able to compile to SMT lib2. But we do that. We also want to state certain things about the code and then use Z3 to prove things about the code. So in this example, we have like a typical kind of ledger or accounts module. It's got a table. The table's type is account. It's a very simplified table. It's basically got a key set. That's the Pact notion of a single or multi-sig authorization. It's got a balance column. for now, that's all, and it's a key value, so you don't have to specify the type of the key. The key is a string, all the keys are strings. So what we decided is, we decided we wanted to use this like at syntax for metaprogramming and say that, which also you can do docs with this. And the idea is that we can specify properties right in the Pact code that we want SMT-lib to prove. So, and we have abstraction in our property language. So at the top you have this def property, conserves mass. This is like one of these like blockchain only terms where people are like, what are you talking about? Conserves mass basically is this idea that like if you're maintaining a ledger and you do like debits and credits, you never want to increase or decrease the total amount of coins in the system. It's basically making it impossible to double spend. You know, like if I debit my account and pay you, I can't use that same dollar to give to somebody else or something like that. The way you enforce that is one way to enforce that is you look at all the coins in the system and you make sure that that amount never changes. And that's what this abstraction def property produces, because there's a notion of columns in the model language. It's pointing it at the table, it's pointing at the column, and it's saying that in a given transaction, the delta must be 0. You can use this column delta thing actually to say that a step function must apply too. You could say that like, you could define a function where the total coin supply needs to increase by 1, and you could prove it using column delta. But here we're going to define something called conserves mass. And then in a function like transfer, which is where the rubber meets the road, we're going to say that a property of transfer is that it conserves mass. And then Z3 will go through and find, if you have a bug in your code, it'll give you a model. It'll just produce the model that says, oh, like if you didn't check that you had a negative amount, for instance, that would break mass conservation. It would just it would say -1. And then you'd be like, oh, my code's got bugs. Likewise, on something like we have the ability to define properties over a schema, which is really a way of defining it over a table. So the idea here is that you can think of these as like typical database constraints, where we say that like the balance column can never be negative. We don't support overdrafts. You know, all amounts have to be real, 0 or greater. So that's a very interesting system. It's the topic of many other talks. The thing we're focused on here is that we have a language within a language. We have Pact, which is define, transfer, arguments, types, abstraction, application, def schema, certain amount of syntax, module, so all the things that make Pact what it is. Then we have this thing called @model that drops into a new world. And that immediately presented some challenges to this idea that we had this parser that was very Pacty. We had this, our Lispy parser, for instance, if it saw something like source string, it actually knew what a string was in the parser. It would be like, oh, that's a type. It would recognize string as a type. It would recognize colon as, in this case, as a type annotation. Like that's a type annotation. So as the model language grew, it started running into these kind of Pact things. So that's what we're doing. We're embedding this, and as I said, the Pact parser was too smart. It was recognizing all of Pact's literal types and things like that. And what we wanted is a parser that was considerably lower level. We wanted something that would basically just recognize Lispy syntax, sexp syntax only. And then, which would necessarily make the compiler have, what we call the compiler have a much bigger job, but that's okay, because now we can just take one of these exps and kind of leave it unparsed and hand it off to the formal verification system and just kind of stay out of its way. So now, Pact parser v2 becomes this incredibly simple thing. It's just got literals, atoms, lists, and it supports more than just Lisp lists. It supports braces and curly braces and separators. And separators is how you could make something like a JSON object, is that you could say, we've got lists, but we also support this thing called a colon. We also support this thing called a comma. So, commas, colons, we have a colon equals thing. That's what separators are: list, atom, literal. Atom is a bare word, and then the literals we support are like, those would be like strings and certain kinds of number productions, Booleans, things like that. Very simple, finished in like a day or something like that. But now we had to look at the compiler. So now the compiler's got a much harder job. or just a bigger job. I mean, given the way we had it with all the pattern recognition, we were basically going to have to throw all that code out because it was starting from much later, so all the patterns would be useless. So the major factor has far less rich X data type to work with. And it really became clear, especially when we were struggling with some of these patterns things, especially when we started recognizing like doc and model and some of these metaprogramming things that were optional. Doing that with patterns is just like, it's horrible. You get this like kind of combinatorial explosion in your patterns. It's just a nightmare. Wouldn't it be, I was like, wait a minute, I did something with XML. Yeah, that's right. Parser combinators for the compiler. What does that look like? So went back to look at my old XML code from 2 years ago. I was like, yeah, I got this. Cursor's pretty easy to write. It's basically just something that holds where you were, you know, at top, at the head of the list, that's nothing, kind of a backwards list. And then just have a stream data type, you know, that should be good enough. It worked for XML, should work here. Immediately, so this is the new def const. Let's compare that to the old def const had a richer X to work with. It had less work to do, and look at that garbage. Now, oh wait, beautiful. I mean, it's just, that's the production code for the Pact def const now. I mean, it's, I'm going to cry. No. You know, so all of these are combinators, arg, term, meta. This is just something that reads from the state. You know, like there's some state that gets built up so that we know what module is being defined, and we build our const. And just huge improvement, much easier to reuse different kinds of things. But that shape, as I kind of animated before, has problems as a parser. It turns out there's a reason why parsers aren't just StateT Except. One, except is just way too blunt of a tool. Just blowing up actually doesn't give you any kind of semantics in a parser. It's basically just, you know, it means, well, for one, it means that you basically have to use try. You basically have to implement your semantics wherever you want them to be for failure. It also makes it very unclear. There's this notion of like committing that we'll get to in a second. It makes it very unclear where that happens for a given alternative. Meanwhile, state, on the other hand, is too blunt. State can do anything. I mean, if you work with state, you know, you can model any statement, but that doesn't mean state's the right choice. Because if you're doing, like, for instance, if you're doing anything that like follows a path or has like a path that's made up of trees, you might want to consider something other than state, because you're going to end up basically with a lot of very brittle control flow logic that you're representing as your data type and state. And that's indeed what we would have to do here to kind of capture the right semantics for how you could parse through a tree and be able to break out into other alternatives and stuff like that. As I said, you have to do try all over the place. The other thing is that I didn't get this far, but it's probably going to be a dog. It's probably going to be really slow, because mainly because of this stuff. That state is going to get so confused, and you're going to have to track so many things that optimizing the code for speed is going to be very difficult. So this is where I finally stop being an unprincipled programmer and say, gosh, maybe I should try to understand what the hell parsers are. Because, you know, I've used parsers, I've never actually cracked them open. I have no idea what parsers do. All I know is that I've looked a little at the code, and oh my God, the code is terrible. I was just like, you know, you look at the data type and you go, and you vow to stay away from it. So parsec, megaparsec, trifecta, autoparsec. By the way, I was surprised when I did this talk, because I expected autoparsec to look just like the other three. It doesn't, but what does it look like? No, it's, there's no, this joke isn't that funny. It's basically, if you've worked with ASON, and you've ever like actually like made the mistake of being like, oh, I'll just write straight to the JSON parser monad. And you're like, oh, wait, no, I don't want to do that. Like, you know, like, I don't know if people have done a lot of JSON parsing, the nice way to do JSON parsing is to do things like with text, with object, so that anything to avoid actually having to write these like failure and success continuations, because it's like, what does that even mean? Like, it's if you haven't like, if you haven't understood all this stuff, this kind of computation is just really weird. It's possible to get used to, though, and it's actually, of course, it turns out there's got to be a reason, right? It's like nobody would do this if they didn't think it was the right choice. And in fact, they look very similar. So you have what I like to call the four continuations of the parsacolypse. Sorry. And they all have the same names, except Ed's code, which of course is uncommented. So we have consumed OK, consumed error, empty OK, empty error. Actually, all the language, though, I'm going to use does come from trifecta and the way they described it. Instead of saying empty, they say epsilon, and I like epsilon better. And it starts with E, so it's close enough. But it's the same ones. It's all the same. It's the same set of continuations. The big difference here in the shape of these things is whether or not they pass along kind of extra information, whether or not they've said that, you know what, we want to know what line we're at, no matter what. Like kind of autoparsec says the same thing. Like autoparsec's like, you know what position we're at? That's kind of always the same. That's not path dependent. I leave that to you to figure out if that's really true. Meanwhile, parsec and megaparsec, as kind of classic parsers and trifecta, or these two, capture all of their state using these continuations. And so the idea is that there's 4 of them. There's commit OK. So that means that your parser recognizes something. By the way, this isn't just total nerd. I just want to kind of motivate this. You will understand how parsers work after this, and you will not be as afraid of writing a parser, because anybody who's written parsers here eventually gets to the point where they're just kind of throwing combinators at it and being like, try, and like, oh my God, why isn't this working? And there is actually a logic to how all these parsers work, and you'll understand it once you understand how what these continuations do. And it really makes the semantics really, really clear, which is a little bit shocking because the code just looks like such a nightmare. So commit OK. Commit is the idea in a parser where you're like, we're really doing this, and if we find an error, we're done. Like, we're not going to go to an alternative. We're going to say, you screwed up, we're going to bail, we're going to present you an error, unless it's in try. But the idea is that a parser needs to have this notion of like kind of committing to a path and saying, you know, you wrote this, that means we have to see this, otherwise it's incorrect and we're giving up. That's what commit means. Commit error is when that happens. Commit OK also means that like when it's done, it won't do the other alternatives, and you're kind of, and you know, you've got your thing, and now you can go back up in your tree or finish or whatever it is. The other two are empty, and I like to call them epsilon using the trifecta language. And the idea is like, this looks good. Let's do something else before we decide that we're actually going down the commit path. And likewise, an error there is what's called a recoverable error. Like, you know what, that's fine. And this is the true mystery if you've ever written parsers, is you're like, why do I need to use try sometimes and not use try other times? Like, what magic switch flips? And it turns out, well, a switch does flip. And that's where you go from epsilon to commit.
Does it still apply to
To what? It doesn't apply to autoparsec. Or Addo not analyzed for this talk. Because I actually only found that out when I did this graphic. But what I will say is that the parser's instances work for Addo. So my guess is that Addo instance has to do some heavy lifting to kind of recreate the backtracking semantics that are kind of hacked into parsers. Because parsers is really written around parsec and that style of parsing. So Addo, I think Addo is probably a superset in the sense that it can support the backtracking semantics of a parsec or a megaparsec, but is actually, yeah, more flexible in some way. But I mean, as you can tell, I mean, just looking at it, it's definitely got a different shape. It's doing something different. It's still these continuations, though, and it was just one of these things like, it was always just one of these things like, we're in Haskell, why do we have to do this? Like, why do we have to write code that looks like this? And this was, at least for me, this was satisfying to realize, no, there's a good reason for it. Because, you know, and this is what I mean, what's the problem? Well, the problem is the code looks like this. You go in and you look at bind and you're like, oh, I get it. No, you don't. I mean, what's going on here? I mean, it's like, it's hard enough to read something like, if you're not used to it, it's hard enough to read something like state for the uninitiated or something like that. Writing monad instances is tricky, and you get used to it. This is another level. I mean, where you have, these are all continuations that it's capturing on, and this is what any of these parsers do all day long, is that they're picking a continuation of this huge data structure and saying, somehow we're doing something, and God knows what that is. But we are going to dive into this code a little. So let's take a closer look, and this is from parsec. So, as I said, there's the 4 continuations. There's commit OK, there's commit error, there's epsilon OK, there's epsilon error. A lot of what you're doing in a bind instance is basically doing some kind of transformation and then reconstructing the same data type. So what we're doing at the end is we're doing the usual kind of like unparser. This is all in parsec-t, and we're putting something back together. So what are we putting back together? We're actually using the original error paths. So errors don't really participate in the bind. Errors kind of just accumulate as they go. All the parser, it turns out, cares about are commit paths, are the OK paths. Those are the ones that get redefined in bind. So what gets redefined? We're looking at 2 of them, so I've broken this into 2 parts. This first one is commit OK. So just hang with me a little longer. It really is going to make sense. Commit OK is where some parser has said, yep, we're going to go down this commit path. So what does that mean? What it means is that it's going to, remember we're binding and K is the action or whatever, K is what is being consumed by bind all the way up here. What it's going to do is it's going to evaluate K. It's going to call unparser. But what it's going to do is it's going to take over the epsilon continuations and it's going to reroute them at commit. So remember, we've redefined commit here. And what commit does, as soon as you go down this commit path, all of a sudden your epsilons are no longer epsilons. They have now been routed to commit OK and commit error. And what generally commit OK and commit, what all these things do is basically build up state to say, oh, we've matched this and here's what we've done. And so the thing I want to point out here is that this is actually really quite elegant in the sense that this is how these continuations actually capture a really complex state path that is very lawful by simply pointing one continuation at another one. And that's it. And we'll look at the next one that gets redefined, which is the epsilon. Turns out the epsilon doesn't do much. The epsilon, if you do epsilon, all it really cares about is making sure that if maybe we had more, one of the things about epsilon is that you can have more than one error. That's the idea, is that you might, if you say you want to recognize string, integer, boolean, you might want to capture all of those so that you can say, here are all the things that I thought you were trying to do. It's a very common error. So that's what epsilon is for. Epsilon merges errors so that you can have a nice error message and say, I think you were trying to do this. I tried all these things before something committed and I gave up or some kind of failure happened. So that's really the role of an epsilon OK. So the real one is this idea that once you commit, you continue down the commit path. And that's, so what does this mean? This means that Haskell parsers want to commit on the leftmost item in a given alternative. It turns out that most combinators are written using the epsilon success. And there's only there's a limited number of combinators that use commit success. And the idea is that once you get a commit success, all of the future epsilon ones will now be part of your kind of committed path and will build up a data structure that you're actually going to hold on to, or it'll actually fail and say, like, you screwed up. So this is the great news for all you trying to write parsers. That's when you use try. It's really simple. If you do two or more things in a given alternative, and for some reason you have to get to the third thing before you know if you screwed up the entire production, you need to put that in try. What you really, the best, most performant parser in Haskell is going to be one that can recognize on the first recognized thing what it's doing. That's the happy path for Haskell parsers. If it can't do that, you need to put it in try. Again, Addo not analyzed for this talk, so I don't know the exact semantics, but I just haven't really stared much at Addo-only parsers, and that's a real reason to use Ed's parsers libraries, that you don't have to think about Addo as a special case. You can just be like, I'll just use Addo, and we benchmarked it. Addo is still faster than everything. You know, like trifecta is the slowest, but it's got the greatest error message. Megaparsec does very well, but it's not as fast as Addo. Addo is still the one to beat, but you don't have to go just into Addo land. You can use Ed's library, and then the point of that in our case is by using trifecta, we put that in our SDK. So if you use Emacs or you use Atom to code Pact, we pass that through the trifecta parser, and you get these nice error messages. Because at that point, that kind of speed doesn't matter. It's fast enough for an IE. In the blockchain, we use Parsec, because by the time you're loading something into the blockchain, it's showtime. If your code has bugs, you should have found them in the SDK. I mean, especially if there's parsing bugs, you should have found them in the SDK. If you're just like live coding into the blockchain, you know, I can't help you. So, back to the problem at hand, which is, this is all great, and this is also how these things are fast, too. This is how some of these things are not total performance hogs, is that continuation passing is also fairly performant. I mean, I'm sure it has its own. I would imagine you could get some horrible space leaks actually in those, but the whole idea is that it's actually that writing these things is hard. You know, doing all the continuation munging is hard, and performance is harder. It's good to understand what the code does, but going and writing it yourself, unless you're Ed, you should probably use megaparsec if you want a rich parser. You should use parsec if you want a fast parser. Like, it's that kind of thing. And my big wish was like, well, gosh, you know, these combinators are relatively general. If only a parser supported arbitrary streams. Well, that's megaparsec. Very recently. Megaparsec version 6, it's now up to 7, but version 6, which is not that old, introduced the notion of being able to parse over arbitrary streams. So you could, that basically the monad parsec is parameterized over a stream type class. And the stream type class specifies two types. One is your token. The other one is what is a bunch of tokens. Like, what data structure are you using to represent more than one token? What data structure are you using to use token? And one little thing I wanted to point out to Haskellers is don't forget that you can do type families and type classes. A lot of times people think type families are these things that you would only deploy kind of by themselves. It's actually the most, if you come from like a language like Java, this is one of the easiest ways to get into type families, is to say that a type class can also specify a type that it operates over, and it's just really, really easy to use. So this is a very logical and straightforward deployment of type families, and the syntax couldn't be simpler. The other thing that megaparsec has, just luckily, is it had this notion of being able to kind of control what the input is. That's basically setting the stream, and the reason why they did is that they have support for include files. So the idea is that, you know, you're parsing through something and then someone includes something. Think about that, you're basically treeing into another file and then coming back out of it. So they did it in actually a really unprincipled and kind of lawless way, which is just get input and set input, just, you know, like, oh yeah, we got a new state now, don't worry about it. Okay. But it does work. You know, you have to make sure that you kind of handled these things right, but I mean, I didn't show you what this type class actually looks like. This type class is actually a disaster. The stream type class, I just had to copy and paste a bunch of stuff to get working on it, but who cares? They've parameterized it, it's polymorphic. I'm very grateful. Get input and set input is a mess, still very grateful. Because source file trees look a lot like ASTs or XML. It gives me the shape I need so that I can do this with megaparsec. The other thing that megaparsec doesn't have, and this is, we're going to get more into this in a second, is one thing you don't do in a char parser is be like, huh, what was that char I just looked at? It's like, it's right there. You know, like, it's right there in your code. It's usually hard coded. So you're usually not being like, I just recognized char. Now, was it char that I recognized? So as a result, one thing these parsers almost never support is the ability to say, wait, what was I looking at? Because You never care in a char parser, it turns out. So this is actually a clue to the big problem I'm going to run into here, is that I need a little extra state just to show whatever exp I was looking at. A lot of times this is just to get like the code position. You know, like, oh, this X parse, that's great, but I still need the code position. So I can assemble my object. But that's it. I took that cursor thing that I showed you before, the simple kind of a stateful AST zipper. Here's how you deploy a type family in a class. Again, I really love the syntax. I think it's just so easy. You know, what is my token type? It's expinfo. Done. Now the rest of the type class is parameterized over expinfo and a list of expinfo. Really easy. I mean, it's super nerdy, but please check this out. This is like, type families are very powerful, and this is just one of the easiest ways to deal with it in a way that won't blow your head up. I have this little parse state. All that is just what we're looking at. There's my monad. It's parsec, you know, monad parsec with a cursor. You can have custom error types, which is they jump shark on. So that's void. Parse state. That's my custom parse state. Beautiful. Oh, we're not done. And I've tried to make this into a joke and like say we're not done over 30 slides, and it just doesn't make sense. So trust me, we're not done. I couldn't like make this into this narrative where it's like, oh no. So you have to know a little bit more about what we're doing with compiler to understand how we're not done. So when parsing sex, remember what we're doing is we're not parsing characters, we're parsing these productions that came out of another parser. We would like, so in this example, we're doing, you know, one of the things, these are 3 list productions here. We have let, here's a let that assigns A to 1, returns A. Here's a production that comes out of Pact and some other lists to import a module, use accounts. These are both special forms. These are not applying functions. These are where in Lisp this would have been a macro. In Pact this is something a compile is going to recognize. This is one of the jobs of the Pact compiler is to recognize some of these syntax productions. There's syntax in Pact, they would be a macro in Lisp. You might wonder, wow, Lisp, everything looks the same in Lisp, a big criticism of Lisp. It's just a bunch of parentheses. Lisp, lots of something parentheses, right? Superfluous parentheses, right? This is application though here, right? So, you know, you have a job to do here, which is, the job is, are we looking at a special form? So here's the parser. We have this construct called with list that drops us into a list. We want to see if we're looking at a special form, one of these guys, let or use. Or we're just, at that point, we're just going to kind of break out to an app plus. So what does special form do? It's got some pretty lucid code. We actually did manual switching here kind of for performance. You know, we wanted to say it's always going to be a bare atom. We'll explain what a bare atom is in a second. And then we're just going to go through all of them and kind of dispatch here. This is kind of just for speed. And then app is actually looks at what we call a var atom in the sense that like the name that is used in an app can be qualified and things like that. So it's one of these things that's real, you know, like it's a significantly different parsing path. So bare atom, what does bare atom do? It basically says that it calls this bare atom, which basically looks at qualifiers. So one of the things we recognize in the parser is the idea of saying like foo.bar.baz. That's what's called a qualified atom. It says, I want to make sure in a special form, you never qualify a special form, like let. You never say something.let, it's always let. So we're looking for that. And then, but what it uses is a very low-level combinator, which is based off of a prism e-atom. In other words, we're basically saying there are only 4 things we can recognize. We're looking for an atom. And so this is the base case. The base case is exp. We have this thing called exp. It's got 4 constructors. We're going to pass in a prism. Does everyone know what a prism is? Haskellers? Lens, if you've used lens, lens gives you these things that allow you to kind of like interact with the data type. A prism allows you to say, allows you to traverse over something and say, if I used this constructor, grab it out of that object. So prisms basically correspond to constructors. If, I don't know where I have. we have our exp. This would have 4 prisms. And the idea is prisms basically give you a way to kind of reason about constructors outside of constructors, to say that like, I'm expecting, say you're like interrogating some kind of doing like what we call train wreck and object oriented. You're saying like, inside this thing, I'm expecting there to be something that was constructed using a list. You use a prism and a lens to match on that. So that's our base case. You know, we're looking at these XPs, sorry. We're looking at these XPs, that's our base case, is we're saying which XP are we looking at? That's the fundamental test that we're going to do on pretty much everything in the system. Are we looking at a list? Are we looking at an atom? Are we looking at a literal? And what this is implemented using is token. This is the fundamental, because you know, it's still a bit of an awkward thing to use something like megaparsec for this, because megaparsec has this huge library that's just all about char parsing that I just throw away. I don't use any of. They have this thing called token. So token is one of the monad parsec functions, and it basically allows you to give it a predicate, and it's where that commit path magic. Remember what we said before, that what parsers do is they want to recognize something and commit to it. That's what token does. Token is what's in other languages, in other parsers like satisfy sometimes is the low-level one. Token is the one that says, I'm looking at, and it's really intended for char streams. You know, like if we were looking for let, it's like, I'm looking for let, I give it a predicate that identifies let, and it says, oh good, we have let, we're committing. That's what token does. That's where this hooks into megaparsec. So the question is, if you looked at what we were doing in special form, we wanted a bare atom and we wanted to match on its name before we can really do anything meaningful to say that this is a special form. We want to see that it's an unqualified atom, an unqualified atom, and that it matches some certain text. So the question is, where does commit happen? Anybody? Atom. Because atom is where token gets called. Or sorry, atom directly calls exp. It gives the atom prism to exp. That calls token. So as a result, all of the rest of these are further tests. So remember what I said about parsers. Parsers want to recognize one thing, and then they want to commit to the rest of them. Atom is way too soon. Like, so for instance, the UX that you get is a disaster. Say a bad let, right? We recognize let, but we committed all the way, basically, like before we even saw the word let. We would discover the error in the commit path for let form, but the error context would be at the top of special form. So we'd be saying like, you know, you have a bad let construction, but it would say an error, something like expected use, let, blah, blah, you know, it would just be like, that wasn't what I was doing. And so then you could just use try. We're back to using try for days. In other words, like all this work to try to get a better parser just went down the drain because now we're back to doing try. So this was kind of a drag. So what is the problem with non-char parsers? Char-based parsers never introspect. That's what's great about parsing, is that text doesn't hold any secrets. Text is like, you know, let. It's just 3 characters. You can recognize it, and you're ready to move to the next thing. So that's what all Haskell parsers are based around, is this idea that, that's what leftmost parsing is based around, is this idea that, oh, you saw something, you know, try to make your parser work so that it can recognize something, and then everything else is down the commit path, like I was saying, right? It really doesn't make sense if you have a more complex object that you need to run a bunch of tests on. You know, in our case, atom unqualified, atom text is correct. And try, by the way, doesn't even really fix, you can't get the semantics you want with try. So, and try, of course, destroys your performance. So now what? Token is the only general way in to make a parsec, and other parsers are the same. They have some kind of low-level predicate that's going to, like, you know, push the machinery through. The solution is, one thing I tried was saying, oh, I guess maybe I won't use combinators, I'll use predicates, and I'll try to compose predicates. And that's just gross. I mean, you know, it's like, might as well throw combinators out. Now I've got a whole new logic. Now I've got a predicate logic, and I'm going to put those together. But, you know, in some cases, I would like committing versions of those as well. So it's like, now I'm going to have 2 copies of everything. Like, one is a predicate that I thread back to X, and then another one is a committing version. It's a nightmare. Yuck. So this is where the hacking starts. So the better solution is to actually redefine the semantics. In other words, controlled commit. So token, I need a token version that stays on the epsilon path. In other words, I want it to be like, okay, 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 I don't know what I'm doing here. Looks good. And then commit. An explicit combinator to do commit. No parser offers this. No parser lets you reach into its guts like that. And then the other, the kind of bigger job is that you have to make sure your semantics make any freaking sense at that point. Like if you're going to offer combinators, you got to start saying whether they commit or don't commit. So the easy part is the explicit commit. So remember we have, remember the 4 continuations of the parsacolypse? Commit OK is the big one. So this couldn't be easier. The way you write a commit, I mean, that's the good news. The good news is that that's all you have to do, is call commit OK with like unit and empty state. It'll have already accumulated all the state. There's no new information, so you use basically like unit and empty and all this kind of stuff. You just go on the commit path, everything's good. This was easy. This doesn't break anything. This is just using the style of megaparsec, but this is my user code. And then just lift it into my particular monad. This is where it gets gross. Basically, this is the only way I can do this. Copy pasta the token code and make exactly one change to it. Epsilon OK. That's the only change. I literally copied all this weird code. It's actually even grosser than this. The errors in megaparsec are really weird. But this is the only change. Literally change one character, and I get what I want. Now, of course, what's the problem? The problem is it's copy pasta. I'll bet megaparsec 7, which is out now, this will break. Like, I'm going to have to go re-copy pasta it, or I'm just going to have to pin very tightly to megaparsec versions. It's a bit of a disaster. I don't really know what to do about this, except that it did work. So this got me there. Now I use this p token epsilon, non-committing. All my low-level combinators don't commit. An example of combinators that do commit. So that's the real question. Okay, well now when do you commit? So things that do indicate state that you're going into that you can't really recover from. One is like dropping into a list, where you're expecting to see a list. That's obviously something where it's like, once you've recognized a list, you're kind of on the commit path at that point. Symbol is like a single path bare atom text, where you just want to recognize a string. You want that whole thing to commit. Another one would be like you want to see a comma. That's what SEP does. You want to see like a comma in a particular place. That's an example of like you were looking for a comma. It's more like a char parser, so that commits. Otherwise, you have to do it yourself. With the kind of drawback that you can't have a pathological parser at this point. You can have a parser that never commits. If you don't remember to call commit, you're going to have an alternative that's really ill-behaved. But here it is in action. So special form now calls bare atom. We know what bare atom does. It goes to atom. It does all those things. None of those have committed. Test, test, test. It gets to testing, this kind of performance improvement to just check a bunch of different strings. And then it commits, and before it goes into the handler. This solved it. At this point, a whole bunch of other bugs went away too. There's a bunch of semantic things inside of the parser that were not making any sense. They all got fixed by this. So we're near the end of the talk here. A little postscript. I wanted to ask any GHC mavens, what in God's name is simplifier text exhausted?
I think it does like
So should I actually mess with that?
You can try, it might pull up right?
Might just try going a little bit higher, that might fix it. It doesn't fix it.
Well, what does it say? It says it's like, does it say what it is? Yeah, default 100? 200,000? Are we really going to set this to 200,000? No, but look, it's already 200,681. 200,681.
Oh, yeah, so that's the packer that they're setting, not the total text.
Oh.
That's the rate.
So basically what was going on here was, the first pass of the compile of this parse over parser, parse thing was actually pretty slow, but I started putting inlines and it sped up just crazily. I mean, the stuff inlines beautifully. But once I got to actually my user code, as soon as, like that special form, if I put an inline pragma on it, boom, the whole thing blows up. And so I know my code isn't as fast as it could be. And I guess my question is, one, why has this never bitten me before? I mean, I've been inlining things for, I've been doing so-called high-performance Haskell for 4 years and inlining things for days. All of a sudden, it might be megaparsec, maybe megaparsec over inlines.
You might get exposing rules. Like, once things are inline, like, it seems that the rules apply to inline code. And then, like, that causes more rules to fire than would have happened before. And so, using it as a
GHC has also modified its simplifier and generally it's inlining stuff quite a lot since 8.02.
Right, there's an old JC. Although,
it's not clear what happened.
well, that was the thing, is that, the very first thing, for a while, it's not looking like we have to be so strict about this now, but Pact runs in GHC.js as well as in GHC, so that meant that we at least needed to support 802 as a compile target. But that was the first thing I thought, like, okay, well, here's our Rubicon, like. But then I found, just doing some Google searches, I found, I think, Vinyl or something. Somebody had opened a GitHub issue on GHC 8.4, simplifier text exhausted. So I was like, I don't know about this. I have a feeling that this is going to bite me. Like, I haven't done it yet. Maybe it'll get fixed. But like I said, maybe it'll be worse. I don't know. All right, well, thank you for that. That was like.
You also choose between inline and inline, inlineable is where that thing, instead of always inlining it's more selective and it can open up optimizations without necessarily having to set a lower. That might help.
Oh, that's one I could try. One thing that's really interesting about this is that I made a library called, I don't know if I have it up here. I made a library called xparser, which kind of had all the general parts of this, like the idea that, I mean, Pact is open source. All this stuff is available on the Pact code base. Let's see if I have it in my can history. Types xparser. So what's interesting, what's just a little bit mysterious about this whole thing, about the simplifier ticks. I guess I can zoom in. See, Emacs doesn't make it so easy. Is there a key command for this in Emacs?
Yes.
What is it? Meta plus? Control X plus? Control X, control plus. Ooh! All right.
After you do the initial control X, control plus, you just keep pressing plus, minus, or 0 to adjust the thing.
I like you. I've been using Emacs since 2000, and I just learned this. Emacs is how I learned Lisp. Noob. True. Not only that, I started on Emacs, so I'm pretty much totally invalid. So this has got inlines. This is what I think is a little bit about this simplifier text thing. This is what I think is a little mysterious. Is that so? This module kind of has the weird token thing, or sorry, it runs the monad. It's got stuff for errors. It's got the context. It's got the p token epsilon. And maybe this one isn't inlined, but like. I'll bet this one blows up if I inline it. I don't want to try it right now, but actually, let's see. Smart compile, any fans here? Sorry, use stack. This might blow it up. The mystery is that, like, I inlined a bunch of stuff in this module, and it didn't seem to be a problem. And it's only when I go to my so-called user code and compile, and if I inline anything in there, it blows up. And that just seems mysterious to me that like, but it might not be, it built. Yeah, so I should do that. Ish. Oh, that was because I had been doing this. I had been like, you know, I wanted to see if the bug had gone away, and no, it didn't. Okay, that's that. So, thank you. Pact is at Pact. Here's where this is, the fab new XML. If for some reason you want to do MusicXML, obviously megaparsec is on Hackage. And this talk, I'll send out this link, but you can, this whole deck is available. So, thanks.
Thanks, Stuart. As usual, we're going to be going to Gatsby's afterwards. General conversation.
What's the address?
It's straight east on Spring Street on the north.